And I really would like to thank him for accepting the invitation to this liquid metal battery seminar organized by the National University of Mexico and the Helmholtz Dresden Zentrum Rosendorf from Dresden in Germany. We could spend the whole time of this seminar talking about Professor Bojarevics, about his curriculum vitae. I will briefly describe it. Well, Professor Valdis Bojarevics has been involved with the research in the fields of computational magnetohydrodynamics and electromagnetic processing of materials. He was born in Riga, Latvia. He got his PhD in 1982 at St. Petersburg Technical University. He was invited to several research groups, and in 1995 he was invited to join the computational modeling group at the University of Greenwich, where presently he is the professor of magnetohydrodynamics. There, he's been involved in industrial collaboration with a number of commercial companies, developed the software package MHD Valdis. Actually, he has contributed to the development of the Master in Science program in Computational Science and Engineering at Greenwich University. He's a supervisor of Master in Science and PhD students. We really would like to thank him for accepting this invitation, and please, Professor, go ahead with the presentation.
Okay, so probably you can see the screen already shared.
Yes, we can.
I hope it works, because I'm using now PowerPoint in a reading mode, because then I can see partially a smaller screen. If I put it in full presentation, it covers full screen, which is not good, because then I can't see any response from this seminar. So I hope you can see it. And today we'll be talking about MHD instabilities in liquid metal batteries and aluminium electrolysis cells. And since the batteries, we worked quite intensively a couple of years ago, but since then, all the funding attempts failed. And now we are working mostly on this aluminium electrolysis field, which is many years already done on this field. And we're continuing on this. This was the reason why I put in this aluminium electrolysis cells, because there's a lot of new developments, which I would like to share with you. And those are partially even not published. So there'll be some really new results. So let's start with these two graphical presentations here, the kind of batteries, which we imagine large scale batteries will be connected in series, and the aluminium electrolysis cells. And there's a lot of similarities as we see further down. Why these batteries are needed? Because the energy storage dictates this need. The renewable energy sources now becoming more and more important, and recent political decisions show that next decade will be really critical for this renewable energy development. And targets that have been set by governments are impossible to achieve without a really fundamental breakthrough in storage technology. And aluminium industry serves both as inspiration and possible beneficiary as well from these mega storage applications, if these will be successful. Now, liquid metal batteries, what is this? This is a kind of simple schematic representation which we use in our publications. This is a new concept for large-scale energy storage, and probably the first ideas originated in publications in Nature by Wang, Ouchi, and of course, Professor Sadoway was behind all of that. And in our opinion, electromagnetic field effects on the fluid dynamics in the batteries will be extremely important, particularly when we go to the practical implementations of larger scale batteries. And in this respect, possibility exists to reuse aluminium reduction plant infrastructure, which will diversify energy supply. And the technology is very well developed for aluminium cells. And since this technology seems to be quite similar with some modification, this aluminium experience can be really used for the liquid battery developments. So in the battery, what we see, they are segregated by density, 3 liquid layers. And this, because these are 3 liquid layers, provides an advantage for fast kinetics, your ion transport and mixing of different species, and long lifetime and elevated current densities. Current densities up to 10,000 amperes per square meter could be achieved in this, and capacities could be theoretically up to 2,000 ampere hours per kilogram. So imagine if you have battery containing, say, tons, thousands of kilograms, so what would be the capacity? The typical voltage for these batteries is between 0.5 and 1 volt. This depends on the materials used. And for these examples, which I'll be presenting down there, there'll be probably magnesium antimony cell used almost exclusively with respective electrolytes. And I will go to the mechanisms, how these ions are being transported and so on. That's not my subject, but that's what we start with this model of the liquid metal battery. So of course, developing these batteries faces lots of design challenges. This is a completely new field. There's a scale-up problem, mass transfer effects, MHD flow, benefits and disadvantages, and of course, thermal balance, because everything should be kept liquid. But because there is a Joule heating, this is helpful. And if we insulate the battery sufficiently, actually we don't need to supply too much. There'll probably be even too much of this Joule heating. But of course, the electrical efficiency needs to be considered. So Joule heating means loss of electrical efficiency. So reducing this Joule heating and ensuring that still everything is in liquid state, minimum optimum temperature is preserved. It's a huge challenge also for this thermal balance problem. Of course, wall erosion, current collector problems, contacts, neighbor magnetic fields, corrosion, all this is very important. And there's a lot of knowledge already in aluminum industry using different inert materials, like inert anodes, like cathode coatings, sidewall coatings. There's a lot of knowledge which could be really helpful for the liquid metal batteries. But let's concentrate on one problem which relates to fluid dynamics. It's interface. Interface between 2 layers. Actually, there are 3 layers in liquid metal batteries. 2 layers in aluminum cells, but 3 layers in liquid metal batteries. So this is top light metal, like in the previous picture here, top light magnesium in this case, then electrolyte, medium density, and the heavier metal, which is antimony in this case, rather heavy at the bottom. And of course, during the discharge or charge of battery, these depths of the layers are changing gradually, but the electrolyte layer is more or less constant. So let's see what happens with these interface instabilities. But first of all, let's consider the present state of the art of the batteries. And presently, the experimental batteries are working something like an 8-inch size, which means about 20 centimeters. So the latest developments by Ambri company and others are just composing large battery containments in containers using these small batteries put together in different ways, which is also quite a know-how technology, how to put them. But of course, it would be much more preferable to go to larger batteries. And then this simple advantage of gravitational sedimentation of heavier metal at the bottom, then electrolyte and lighter metal would be taken to advantage. But then this interface and MHD problems should be really well understood and solved. So let's see what happened with aluminum cells. The initial cells, more than a century ago, developed 150 years almost, were very small ones and very much resembles what we have here today about liquid metal batteries. Nowadays, so this is about something like a modern cell, these cells, each aluminum cell, are all covered. You cannot see very much, you cannot see definitely the liquids, But it's all these supply bars of electric current. You see how huge these are, because the total currents are sometimes 500,000 of ampere. 500 kiloampere is a typical modern cell. And the cell size is about a small swimming pool, about 20 meters in length. So each of these cells is about 20 meters in this perpendicular direction, about 5 meters in the width. But the depth of the liquid metal and liquid electrolyte is very, very small. It's just about 4 centimeters electrolyte and 15 to 20 centimeters of liquid metal. So you see immediately how this plant operates. There are a series of these cells. And sometimes you cannot hardly see the end of the line because it's about 1.5 kilometers, something like 2 kilometers long in the modern plants. So you can see the scale of that. And imagine if that works for energy storage, what huge energy can be stored. Okay, let's now see how this trend in modern aluminum industry can affect the knowledge of liquid metal batteries. So if you compose liquid metal batteries, say in a container, lots of these, just a schematic representation here. And alternatively, something similar to aluminum cells. You can say, oh, magnetic field will be large because the electric current is passing is total current, 500 kiloamps for this electrolysis cell. Then the total magnetic field surrounding, then according to the Ampere's law, will be something quite considerable. But in these small cells, each individual current could be much lower. But what happens with the magnetic field? When you arrange these cells in the container, the magnetic field is superposition of all these small batteries. And again, you have, according to the Ampere's law, total flux of magnetic field equals to the total current passing through. You have, again, the same situation, very similar. So the total magnetic field is, again, very similarly large. And this could affect MHD process. Let's go first. See now the similarity to commercial aluminum production. So this is a complex busbar used in one of the commercial cells. And we have developed this software for predicting electric current distributions, magnetic fields, then fluid flows, some thermal responses. All these busbars are being heated and the resistances are changing with the temperature. There's a lot of effort. And most of all, most important, the liquid metal interface shape is subject also to the stability problems. And solving these MHD problems is our main task, developing the software, which is somebody gave this name MHD Valdis. And so it's stick for the time. And so this software, we work about 20 plus, more years, collaborating with industry. And there is a lot of validation by measurements in operating cells. And so that's the software we'll be using in describing a lot of effects here down. So the interface waves, how they develop. If you have the three liquid layers, liquid metal battery, so typical densities here, then that's the top metal, and this is the bottom metal. And then the electric current with associated magnetic field are intricately involved when the waves start, because the magnetic field and electric currents are redistributing. And the interaction results in a wave frequency shift. So original gravity wave perturbation, say mode 1,0 long sloshing wave, when this magnetic effect and electric current will be accounted for, the frequency will be different. And the purely hydrodynamic gravity will still kind of serve as initial perturbation, but eventually they give way to new eigenvectors and eigen solutions like a frequency. So this frequency is different and eigenvectors are now being combined. But what we learned is that the square and circular cells are almost always unstable because this mechanism of MHD instability is the most easy to develop in this case, and there is this square, not elongated, or circular cells. That's in horizontal plane. And the horizontal circulation also exists. It's called so-called electrovortex flow, sometimes called. And because of the waves, this vortex flow is also unsteady, turbulent, because the Reynolds number is sufficiently large, at least 10,000 or more. And interfaces and the interface shapes are affected by these circulation velocities, horizontal velocities in these large-scale cells. So the basic wave equation here can be developed in the approximation. As I mentioned, that these horizontal dimensions are much larger, 20 meters, 10 meters, something like that. And compared to the small depths, which is about 5 centimeters, 15 centimeters, something like that, and the small amplitudes of the initial waves, it permits us to develop this modified wave equation. Modified wave equation, you can see it's a second derivative, it's an interface, both for the up and bottom surfaces. And then you can see that there is a kind of friction term involved. I will not go in these details, those are available in the publications, and the divergence term of the interface. And apart from this, there is electromagnetic force, which is not just symbolically represented here. This is horizontal force divergence actually here, but also the Z component of the electromagnetic force could be accounted for in this formulation. And the third term here in square brackets is the nonlinear effect of the horizontal circulation velocities, which I mentioned, those turbulent large-scale electrovortex flows, which are coupled to the waves, are also affecting the waves as a back reaction. So the waves are affecting this horizontal circulation, and horizontal circulation will affect the waves. And of course, this equation then is just symbolic. There's a lot of more statement needed to fully formulate, but we will not go in this detail, just to give you a general impression here. Now, if we start first testing the model for liquid metal batteries for pure gravity waves, no electromagnetic interaction, then what we can see, if we perturb the top surface, then there is this kind of gravity wave, a regular gravity wave at given frequency. This is the first mode. But the bottom, because the metal is so heavy, practically doesn't feel the top perturbation. Now, if we perturb the bottom, give this initial perturbation of the 1-0 long sloshing wave, of course, the frequency is quite different in this case. Then the top wave is also excited. So this is interesting. The top surface didn't excite the bottom, but if we excite the bottom, the top is excited as well. And now you can see the Fourier spectral representation. The blue line and the red line are here matching. So at this frequency, the top surface is oscillating, a combination of these two frequencies, but the bottom is oscillating only at this self-oscillation frequency. Now, if we put perturbations on both of them, then of course there is a mixing of this, and you see the responding Fourier spectra. But that's interesting observation that waves are coupled mostly because of if the bottom is perturbed. The top perturbation doesn't affect too much the bottom surface, but if the bottom is perturbed, it also affects the top very much. Now, let's go to the MHD model. Of course, it's tempting to linearize it initially. And in that case, we can reproduce this wave equation like an eigenvalue problem. In this case, it's still in the time derivatives representation, but further down, we will go to the eigenvalue problem. And then we have the interface wave is interacting by this interacting full matrix GKK pram. This is a complex interaction of magnetic fields. So you see the magnetic fields, different components. You need to decompose these magnetic fields because the full distribution, not only this usually used stationary and uniform magnetic field BZ component, which is important, but the full distribution. And we will see in the real cells, we have really the magnetic field is very far from the constant point. It's distributed, and then this distribution of magnetic field is really important. And this kicks in this term of this coupling term between interfaces in this equation. And of course, we can now compose the eigenvalue problem by representing this H or zeta function like exponential dependence on complex amplitude. And complex amplitude can be decomposed in real and imaginary part. And you can see here that in this way, the real part will be responsible for oscillations and imaginary for the growth or damping of the wave. Now, this is an example of lithium bismuth battery in this case, which is destabilized at certain, in this case, it's using a constant magnetic field, about 20 Teslas, but you see the interface wave, how it develops and what the frequency. So this was the initial perturbation, simply the 1, 0. And then the final wave was the interaction of two strange modes, which initially were by far not present, only this was the initial perturbation. You see 2, 1 and 3, 0 were developed. And you see how it happens, it's not immediate. So if you apply simply a linear stability theory, you are here at the very beginning, at time 0. You are not here. You need quite a long and probably non-linear interaction. And you see it took about 500 seconds when these modes, dominating unstable modes, start interacting. So the linear stability theory, which works at the time 0 moment, is a bit misleading, to my opinion. So you see this full simulation, numerical, of long model showed, but let's go further and see if there's still any use of this linear stability theory. Now, there was a lot of attempts. I even don't dare to say how many papers to explain the interface MHD instabilities, in this case in aluminum cells, and now in liquid metal batteries as well. I will just mention a few very basic oldest papers like Urata, this is initially in Japanese, and then Sele, simple mechanism, Urata extended mechanism, and then Sneed-Wang, Bojarevics Romero, our own paper, which was actually submitted 2 years before the publication, took a long time. And then, of course, Davidson-Lindsay paper, which many people prefer to refer to. And then finally, our latest paper in GFM in 2018, where we put this model in the liquid metal battery context, but also equally applicable to these instabilities in aluminum cells, because this is just a particular case. And also, I would like to draw your attention to this publication in TMS Light Metals, where we used a full verification using measurements by wireless sensors of the unstable wave development. And that will be represented further down. And see, this is probably also quite important for me, this publication, because this gave us full experimental validation, detailed of how the frequencies respond, not only just the observation with stable, unstable, but what exact frequency is being developed. Now, let's see the example. This is very small magnetic field, just about Earth's terrestrial magnetic field, BZ. It's about 2 times terrestrial magnetic field. And you can see the simple gravity wave at 1, 0 perturbation frequency starts already developing some additional modes. And you see this mode, response mode, is still stable, very small, but you see this wave, it starts kind of becoming skewed, because the normal sloshing wave would be just a symmetric up and down, sloshing down. It's now damped, you see, about 1,000 seconds, long time. It's many, many oscillations, it's damped. Now let's go to the next slide. Slightly raised magnetic field, 5 Gauss, very small still. But you see, if it is the same commercial cell example and constant magnetic field simplicity, you see the wave now starts resembling something like a rotating wave. That's how it's actually computed using our software for direct simulation. Now let's see now unstable case. We go to 10 Gauss, still not very large field, but that's enough. And you see this red line. This is how instability develops in comparison to the previous ones. Now let's go for the case of square cell. If we have not elongated, then even for very small 0.1 millitesla, that's the same 1 Gauss case, you see here the interface becomes unstable and the frequency is shifted, and this starts growing at this shifted frequency. So the square cell is almost always unstable. Now let's see how this eigenvalue problem works. So we need to decompose liquid battery problem. We have two wave equations which are coupled together. You see H1 is coupled to H2 and also to the horizontal velocities, to the force distributions, to the magnetic fields and so on. And electric potentials in two layers are also coupled to these interfaces. So you see, we have actually four equations. Then we use this Fourier decomposition using cosinus decomposition, which is more general in this case. And then also the eigenvalue problem is obtained using this exponential. In this case, slightly different. Nu now is given without the imaginary unit here. Pay attention to that. But that doesn't matter because it's still the complex mu eigenvalue. But in this case, we have non-linear eigenvalue problem effectively, because if this linear term is present, then the square eigenvalue is also present. And in a matrix representation, these are full matrices representing these four equations, and also this representation in the double cosinus representation. So you see, this is a rather involved complex eigenvalue problem, and also giving us eigenvectors, which is most important, because then we can detect which modes are really involved, because when we solve and obtain only the eigenfrequency, we just know at this frequency something happens, bad or good, but what complex eigenvectors are involved, we also need to solve this problem for eigenvectors. And we can see which models actually are interacting. Now let's see simple case again, the simple one constant magnetic field. And now again, pay attention to this imaginary unit in definition here. Sorry for that. But then you see that when the laminar damping coefficient, like given in Landau-Lifshitz for this shallow layer, is used, it's almost always unstable. Laminar is not sufficient. We need to use this turbulent damping coefficient for real cells, because this electrically induced vertical flow actually always produces turbulent flow, even in these small batteries. And then in this case, you see what happens when we increase gradually the magnetic field. So from 0 to 2 milliteslas in 0.1 millitesla increments. Then, for instance, eigenvalues are moving here, the dots in this is the largest period dots. You see these dots with increasing magnetic field are gradually moving. And from the right-hand side, they're also moving. And then on some critical bifurcation point, these dots are moving in imaginary plane. And from our purely real eigenvalues, we have now imaginary components, which means that now we have either exponentially growing or exponentially damped eigenfrequencies. So you see at the critical magnetic field, this transition, resonance transition occurs. But actually, for some frequencies, it's almost immediately unstable here, for instance, for this one. So we need this turbulent damping coefficient when the situation dramatically changes. And now you can see almost all these previously unstable, like this one, for instance, is moved to the stable quadrant of this eigenvalue space. It's moved to the positive eigenvalues, so it's damped waves. But at some critical magnetic field, this very largest eigenvector length eigenvector is becoming unstable. You see the first indication of instability happens at this position. And this is the culprit responsible for the instability. And you see the frequency is completely different from what we had in initial gravity case. This, for instance, this, and this, there's a couple, two frequencies. And in this case, it's completely different. And detecting this frequency helps us to establish which modes are involved. Now, in that paper, GFM 2018, we managed to develop kind of analytical criterion, which also includes this friction coefficient, which could be this turbulence friction coefficient, or empirically obtained one. And then knowing this friction coefficient and these interaction matrices, we can determine the critical value when this number here exceeds this damping coefficient value, then instability sets in. So this means that increasing magnetic field, for instance, or increasing current densities, or reducing the layer thickness, and so on, all this is involved in these complex formulas. You can find the full representation of this GFM paper. So, and this is the matrix representation of magnetic field distribution, rather complex, but I will just show you some examples. So if we apply this analytical criterion to some known solutions, and this is the analytical criterion is predicting this critical magnetic field in milliteslas when the instability happens. No wonder this corresponds also to this, our old paper with Michel Romerio, and also quite close to Davidson-Lindsay. And Sneed-Wang is not too far away, but the old Selé theory, which many people are referring to the correct one to predict instability, gives quite a wrong 10 times larger number. So it's not really a good approximation. Now let's see how this analytical criterion could be even applied to commercial cells. So this is a commercial small scale, 180 kiloamps only, but it is pretty MHD unstable. And you see the very complex busbar arrangement. This is the magnetic field distribution, and we can use now this full matrix representation for BZ magnetic field. And you see what happens when we directly compute the interface wave model. When we have sufficient ACD, anode cathode distance, this is simply the electrolyte thickness in the initial stationary state. Then the certain wave, giving initial perturbation at 1, 0, develops at this MHD activated frequency. And if we compare this frequency to the measured, to the paper which I mentioned, then you can see the frequency is quite well matching. And then at some electrolyte thickness, when we reduce this electrolyte thickness, attempting to save energy, say to 4 centimeters, the cell becomes unstable, and you see the frequency is shifted from this one, and you see the numbers here, 246 and 237. That's for voltage and for current. But exactly this frequency was predicted and also measured when instability set in the cell by these wireless sensors. That was very encouraging because this is not trivial how this frequency develops. It's somewhere from this 1, 0 here, it moved to this one at different frequency for stable cell or unstable cell. And then this is kind of confirming our theory. This shows what happens with the velocities. So these are horizontal cells, horizontal vortices in this electrovortex flow. And you now understand why this is a turbulent flow, because this is about 10 centimeters, 15, 20 centimeter velocities and large scale. So this is a really turbulent flow. And also notice this dome-shaped interface station on the background of which the waves are developing. So this is a stable case. And then when we apply this kind of direct numerical simulation, we obtain these two starred, this small star here is for stable cell, and this is for unstable cell. You see then is different ACD, electrolyte thickness, 4 centimeters here, and 45. So at 45, we get this numerical solution for stable cell, and this one for unstable. And what is our eigenvalue solution from this analytical solution, showing that indeed this one is below the stability limit. So this is the largest stability here line. So this one is below, so it becomes unstable. And this one is above, so it's stable. So indeed, these measured and full numerical simulations are quite matching the analytical predictions from this simple analytical formula. Not very simple, but still analytical. So let's go to the next slide and see how this instability develops. So you see, this is showing, it takes quite a long time to develop this instability. It's not instantaneous. And the final picture looks like that. So you see the heap at one side, and because of this dome shape, it hardly resembles this rotating wave. It's more like a sloshing, a bit of rotating at the top. It's a rather complex interaction. And this is, remember, confirmed experimentally. Now, this dome-shaped effect, if we work without this dome-shaped, like in this case, we obtain quite different situation. So you see the interface is still developing, and well, you see this this is a stable case. and dome effects. This is now, yeah, this is still in shape still. Okay, let's now see, we have seen that using this analytical criterion sometimes gives very good predictions for the cell stabilities. But now let's go to the real batteries, which could be made using this idea of modernizing aluminium cells, even smaller size, 8-meter size cell. If we arrange these in series, and then we have the electrode and electric current distribution inside, you see this three-dimensional solution here. And then what we got in this case, the top magnetic field looks like that. So there's quite considerable field. You see quite, the BZ is quite large in the corners of here around. And we see there's dependence also how we arrange these current supplies. If we account for the full circuit, which is absolutely necessary, then we see the magnetic field is this one. And when we do not account for this, then there is different. But let's see, it's smaller when we do not account for the return current. And let's see how it affects the fluid flow, these horizontal circulations. So you see this first one is with this return circuit, which is now unsymmetric, one large vortex dominating. And here it's quite symmetric because there's no return line and the vortices are quite different. And also notice the intensity of the flow. Now it's 20 centimeters, 15 centimeters for this type of cells. So now this is the most unstable is magnesium electrolyte, magnesium and electrolyte and interface. And now you see this beneath the electrode, we get this development when the current is concentrating. You see this kind of heap of a liquid metal going up. And this leads to this. So you see the bottom is stable, but the top is oscillating at constant frequency. Now let's magnetically optimize and apply the same structure what we used for these aluminium cells. But now let's fill these aluminium cells with 3 layers of liquid metals, like magnesium and antimony, and electrolyte respectively, and see how this will affect the stability of such cell. Because we saw that that simple cell appeared to be quite unstable. But now let's use this knowledge from aluminium electrolysis cells and use the busbars in special arrangement. And now we can see that this is the current distribution in this cell. And now this is a comparison. The simple cell, one electrode, and this is the trimet-like cell used for this liquid metal battery model. And you see the magnetic field is considerably lower, BZ, if you compare here, about 4 times. And the velocities developed in this case are in 3 layers. That's the top metal. You see it's not very large velocity in this trimet cell because it's optimized. In electrolyte also we have some horizontal circulation. And at the bottom we have also not about 7 centimeters maximum. These vortices are existing there now. Now, if we now impose, say, rather large electrolyte perturbation at 100 kiloamps, very large current for this liquid metal battery, and then we compare the simple cell and trimet cell. And you see immediately that this trimet cell, which is magnetically optimized, is just becoming, this red line is just becoming stable. What we cannot tell about this simple cell, even for this very huge electrolyte thickness, 8 centimeters, it's still oscillating at constant frequency and constant amplitude for a very long time. So you see the top and bottom oscillations here as well. The bottom is more stable and the top is less stable. You see these oscillations here. So I will not delve more in this. And now let's go and see what more knowledge we can get from these aluminium cells. Aluminium cells are quite modified. Each company has different arrangement of these busbar supplies. And modern cells are particularly intricate. And here you can see our model, how it works to predict electric currents in our generic 500 kiloampere cell. And this shows the electric current distribution and temperature. So this one is electric current distribution to the left, and this is the temperature distribution. You see different bus bars are at different temperatures, so their resistivities are quite changing, because some of these bus bars are heating up to hundreds degrees, 150 degrees, 100 degrees. These aluminium bus bars, which are massive, sometimes 40, 50 centimeters in cross-section size, and then 500 kiloamps, that's huge current, needs to be supplied. Then all these external circuits of electric current are extremely important. Apart from that, we need also to calculate the electric current inside of the cell in liquid metal layers. And this shows two different cells. One is a kind of commercial cell, one of the cells we have in our experience. And this is our generic cell, which we use for a lot of experiments for demonstration purposes. And you see there is a large horizontal current going outwards, because these collector bars are collecting here at the outside perimeter mostly. There are a lot of tricks how to reduce these. The commercial cell, it has more distributed bottom current. So this is at the bottom, JB is bottom current in color, and arrows show the horizontal. And the horizontal, when these bottom currents are more concentrated at the edges, there are larger horizontal currents, and larger horizontal currents are bad because they produce more circulation, more interface deformation, and also affect this dome shape. So commercial cells are designed both to optimize the magnetic field and these electric current distributions. Now, next is the steady state MHD result for magnetic field distributions. And in metal pad, we have magnetic field in the Z direction, vertical magnetic field, for this generic cell, and for the, and actually this is three-dimensional, this magnetic field, even in the metal layer at the commercial cell, or generic cell in this case. And at the top of the metal, we have one distribution, and at the bottom of the cell, liquid metal, which is just about 15 centimeters, not too much, but it's a fully three-dimensional magnetic field, which is accounted in this model. And you can see that the magnetic field is rather well optimized, and the maximums are about 10 Gauss, 18 Gauss something, but this is just localized subregions. Now this is for the commercial cell, which is even better optimized. And now notice here that magnetic fields at the top, for instance, where they pay most attention, is much lower and concentrated in just a very corner on this large. But the middle part is just around very, very small values of magnetic field. And similarly at the bottom part as well. Now, the steady state MHD result shows that there are flows developing these electrically induced particle flows, but actually these are interaction of the electric current from this passing through in liquid bus, liquid electrolyte, and liquid metal, and interacting with this three-dimensional magnetic field. All three components. I was showing previously only the BZ, which is essential for the stability, but for these circulation patterns, also this current interacts with the BX and BY horizontal magnetic field components, which are very considerable in the cells. So you need to account for all three components of magnetic field to obtain these circulation patterns. And you can see that liquid metal flow is different at the bottom in the liquid metal and in the electrolyte at the top. Now, the next slide shows the interface deformation when this dome shape is accounted for. And now you can see that vortices are really interacting with the dome shape, and the dome shape is different and vortices are different in this in our generic cell and 500 kiloamps and commercial 500 kiloamp cells, which is better optimized. And now you can see what happens when the transient wave develops. Actually, the magnetic field and electric current are now changing. If we have this initial sloshing wave, then there is elevation, and this horizontal electric current flows along the cell, choosing the bottom cathode collector bars where it's easier to get out, and then from the top, it passes through and goes in liquid metal in horizontal way, quite a large density. You see the density is now 31,000 amperes per square meter. It's very large density. And what happens is actually this electric current, which flows horizontally, 500 kiloamps total current, produces quite considerable magnetic field perturbation. And you remember I showed you initially the magnetic field in this commercial cell was just in the corner. But now with this perturbation of horizontal electric current interacting, the self-magnetic field of this passing magnetic current, electric current in this liquid metal produces this additional perturbation magnetic field, which oscillates with the interface. So the electric current oscillates, interface oscillates, and the magnetic field is oscillating as well. Now, the transient model predicts that this cell will be stable up to certain anode-cathode distance, something like 35 millimeters. But at 30 millimeters, so this greenish line shows that the wave starts growing. So you see this is constant growth. And so this empirical friction ensures that even that cannot damp this one, the turbulent friction. And the frequency which develops is happening, this unstable frequency for this 500 kiloamp cell happens at this particular frequency. But you see the ACD is pretty small, about 30 millimeters, because this cell was very well optimized. Now, transient MHD results again. What happens when we account for this magnetic field and with the dome-shaped interface? And so you see again the same story, that now with the dome shape we have, and this dome shape happens because we have these open channels at the anodes where the gas is being involved in. So the pressure distribution is better distributed. And let's jump further because our time is running out. And now we can see that if the magnetic field is actually time dependent, so very computed, we have different oscillation pattern and different slightly frequencies here. Now we can see also the coupling which happens. So this is the busbar arrangement, how the electric current is supplied. And for this cell, you can see this is a commercial cell, 300 kiloamps, that the interface, dome-shaped interface, it's a stable one. So you see, but it's still oscillating long time, about 1,000 seconds, about 17 minutes it means. You see this oscillation and this interface is moving, and also the fluid flow velocities are slightly changing with that one. But that's a stable cell. Now, when we include this dome shape for the unstable, you see how much these velocities are involved and interact with the dome. Now you can see here the horizontal circulation effect. You see that without this horizontal circulation effect for this particular cell, we had this frequency. But with this horizontal circulation, turbulent flow included, we have quite different and more stable two frequencies developing. Now, new ideas are recently developed how to stabilize these cells and even push the ACD even lower. This publication where I am indirectly involved, not my name in the authors list, but you see Doug Kelly from Rochester University had this idea that they want to simulate the metal pad instability in a commercial cell where we proposed our TRIMET 180, well documented, using this software, because they were discouraged using ANSYS and COMSOL, which were not able to predict these long-time wave developments. And what the idea was that parametric instabilities can often be decoupled by introducing a new frequency, by imposing some kind of perturbation that frustrates the resonance of this unstable MHD wave. So they have hypothesized that adding an oscillation to the current would prevent this metal pad instability. And so what they attempt in their paper is the steady 180 kiloamp current was supplemented with an oscillating component of magnitude about 20 kiloamps at the given specific frequency. And the standing gravity wave driven by the current oscillation now frustrates this oscillating wave that comprises this metal pad instability. And what, so you need to read the paper, we demonstrate very nicely. It's possible to indeed damp the magnetic instability by this method. But we went a bit further. Instead of the full current, only additional current loops now are modified. So we put these green additional bars here. And you know, nowadays there's a special technology where you can put even superconducting bars at special insulated cases. And the cost of passing these currents is very, very low. And you can pass, say, the same 20, 40 kiloamps in these additional bars and modulate only those, because modulating the full current in the cells is kind of counterproductive to our opinion. And in this case, you see the view from the top, these additional sidebars are supplying just modulated magnetic field for the cells. But the cells work at the same normal current as before. So the response of the normal cell would be like that one. So there's a critical ACD. Very difficult to see here the numbers, but hopefully you can see them. So there's a critical ACD about 40 millimeters when this instability starts growing. And you see the frequency shift here between the ACDs are very small because the magnetic itself, we start the initial perturbation as usual with 1,0, but it shifts to this frequency. Then adding this compensation busbar and frustrating this instability at the unstable, this larger one, which was unstable, and adding additional frequency, say this one for 0.0, this is the period 22 seconds. We almost managed, but not completely, to suppress the instability. And then if we optimize further and find the correct frequency, in this case, it's this one with the period about the same 20 seconds, but very correctly optimized. We see what happens with the oscillation. The black line is the oscillation of interface. It oscillates at very, very small amplitude, like the stable cells here. But actually, that's an unstable ACD. So what we managed here, we managed to stabilize the interface by adding these perturbed busbars, which give this perturbed magnetic field at this very specific frequency. And you can see here the red line is the electric current in the busbars, and this blue line is the magnetic field perturbation. But the resulting interface now, and you can see also the frequency. This now, the interface and also the electric current is at the same imposed frequency, not at the unstable one. You see the unstable was happening at this one. And here, you see the unstable here is still pushing out, and this imposed frequency was not able to completely suppress this instability. But if we correctly choose this frequency, then this parametric instability is able to suppress. The cell is now oscillating stably at very small frequency, and you can work at significantly lower ACD. One more problem I would like to tell you a couple of words is this aluminum dissolution, which is very important for aluminum reduction cells. And you can see this aluminum dissolution is needed because alumina particles are gradually dissolving. It dissembles also the ion transport problem in liquid metal problem. This is why I'm liquid metal batteries. But the aluminum dissolution is very important for aluminum production. But ion transport is also affected by very similar effects. And what we do here, we account for these dome-shaped or these circulation effects. And when we have the dome shape, then the particles are affected by additional biomancy forces and also some Wien-of-Kohlen electromagnetic forces and so on. But then the concentration of the dissolved alumina now is controlled by particles traveling in the liquid bath, in this case, electrolyte, and also the negative source is the metal production or the ion transport. In that case, the ions are being transported at constant rate. Not constant, but depending also on the current distribution, how the current is distributed at the cathode surface. And then these terms are, what we couple here is dynamic track of the particles of different sizes. And the source term is affected now by these particles being dissolved in the concentration field. And in this case, we have two different examples, regular cell and end-of-line cell. So this is the important because then the velocity fields are quite different. And just to show you some examples. So this is the depletion of alumina when feeded at certain intervals, about 120 seconds, certain amounts, and the feeders are located in specific locations. And you see after optimization, we obtain, when the feeder location and the periodicity is optimized, we obtain much better distribution of this alumina, and also the ion transport. If the cell is perturbed, being at the end of line, where the magnetic field is different, you see different flow patterns, and also these distributions of the particles and concentrations. So the rafts of particles forming, it's about long time distribution, up to 2000, even sometimes 3600, 1 hour. This feeding and ion distribution is being modeled by this model. So we can finally come to some kind of conclusions. So liquid metal batteries of an industrial scale can be designed to satisfy MHD stability conditions when reusing that infrastructure knowledge available from aluminium plants. And for cells meeting practical cost requirements, the bottom heavier metal layer will be always quite stable, but this top light metal interface is the critical one to control. And I believe I have finished my lecture today, and thank you for your attention.
Great. Thank you, Professor. So we are just on time, so perfect. We still have a few minutes for questions from the audience, so please feel free to ask. Are there any questions?
May I ask something,
Please,
Alberto?
please, go ahead.
I just wanted to ask Valdis, are you still working on the liquid metal batteries, or do you see, I don't know how it works in England, do you see some possibility to get funding for these things? Because I think in Germany, we switched then to the small batteries basically to get money, but for the large batteries, it was already, for us at least, it's quite difficult to achieve funding, for example, for these large things or for the interface instabilities. How does it work for you?
Yeah, and it doesn't work for us as well. All attempts obtaining funding, and you know the fate of this European funding and then British funding, nothing worked. And so presently we are not continuing research on these batteries. We are continuing only on aluminum cells, where there's a lot of commercial interest, obviously. And so this is where we put our most efforts last couple of years. And I lost my student. He is now somewhere in Tokyo, and Tokyo University. And then, but I'm continuing work on these aluminum reduction cells. And as you can see, there's a lot of developments, quite practical developments, which obviously could be implemented in liquid metal batteries as well. That's my response.
And Andres Tux is now in Tokyo? Or
yes, last what I heard from him, he is a kind of not some institution in at the umbrella of Tokyo University.
Okay. Thank you.
All right.
Thank you, Norbert. Any more questions from the audience? I would like to briefly ask you, all these simulations are based on the solution of the magnetic induction equation? Or,
yeah.
Okay, great. So for the boundary condition of the magnetic induction field, you will need to consider extra volume, extra air domain?
Yeah, my answer is that that's what ANSYS, COMSOL, and finite element methods are using. But we definitely are deviating from this approach. We are using very sophisticated Biot-Savart representation, where we account for distribution in volume, even in busbars. In busbars, we use some kind of simpler Biot-Savart, but when we encounter the observation point and the measurement point are the source and observation point are coinciding, there is a singularity, then we need to kind of resolve this singularity. And this is all very efficiently implemented in this code. And so all the external bars with varying electric currents and internal electric currents also produce magnetic field, a very considerable magnetic field. And thirdly, there are ferromagnetic parts, which are non-linear. And all this is included in the code. And you can look at our publications in typically light metals, where with different kind of results are being presented. It's very complex magnetic field, which is rather accurately computed using this software.
Thank you. I will look for those papers. Sergio, it seems that you...
Yes, if I may ask something. Well, Valdis, thank you very much for your nice talk. It was really very interesting. All your simulations were done for this rectangular geometry. And it appears that for large scale, if we think in getting this large scale in liquid metal batteries, that would be the proper geometry, if I understood correctly. But in terms of stability, so could you say a few words about comparing this geometry with respect to the cylindrical geometry in liquid metal batteries? Have you done some experiments on the other geometry?
Yes, definitely cylindrical is much less stable, because then the mechanism, the classical Saleh mechanism, will immediately kick in and nothing precludes that. Just the stability of these cells will be very, very suspicious, and very low magnetic fields will be initiating, and the instability. So there's no much sense. Nobody in aluminium industry uses cylindrical. Nobody, since the first invention by Héroult, when probably they were cylindrical, but immediately they switched to these elongated, and it's much more practical, and only the stability can be achieved in these. And also for production purposes, rectangular, just packaging and other reasons, it's from practical point of view, the cylindrical are not recommended. And industry is not interested, absolutely not, in cylindrical.
Okay. Okay, thank you very much. Thank you, Valdis.
Yes, please.
More questions from the audience, maybe?
May I ask something?
Go ahead, please.
Valdis, do you remember some years ago on the workshop we were discussing about small scale interface instabilities? And basically we had Sabrina Bernard in Dresden for 1 year working on these things. And when we wrote the paper for her, I tried to go through all the literature I know about liquid metal batteries. And we basically found 2 things, or let's say 3. At the MIT, all the experimentalists, they were writing down their in a lab book, yeah. So I read all the lab books, and I read really a lot that they built cells and they had to short circuit, but they could not look inside these cells, so they didn't basically know why they got such short circuits. So this means basically short circuit is important. And looking in the other literature, we found one article where they wrote that they found small, let's say, metal droplets inside the electrolyte. So really small bubbles, small droplets, and they don't know why. And the third thing was intermetallic phases. Intermetallic phases, sometimes they were growing like crystals and then going through the electrolyte, short-circuiting it. And this means altogether we don't have much evidence for We have evidence for short circuits, but
yes,
no
I
one
would like to
happens.
comment on this. Yeah, we
Yes.
definitely need to avoid these because the lithium batteries are got a very poor publicity because of these short circuits. You know what happened. If something happened like that in liquid metal battery, that will be equally devastating. We definitely need to avoid. But from mathematical and experimental and just for knowledge gain, it's really interesting what you put in your paper. And actually that paper resembles me very much results which we ourselves obtained for vacuum arc remelting. The situation is very similar. There's a liquid metal film, but then we need these droplets dripping down. And what happens is when the electric current is passing in this vacuum arc remelting, and when the droplet forms, it concentrates in the droplet. And then it helps to detach the droplet. And also recently I was involved in one German company in this large scale vacuum arc remelting. It's about almost a meter size electrodes, and on the bottom was liquid metal film. And then this detachment of the droplets played a significant role. And the proposal was to rotate the electrode, and then these droplets are moving more to the periphery. And if these are in the center, it's really devastating also for this vacuum arc remelting technology. And other application where these droplet formations I encountered was a droplet generator. We attempted in Japan, Tohoku University, to create a silicon spherical droplet production. And then we used an inductor to pinch off the droplets from the small orifice emanating jet and introducing this perturbation. And what we observed there, that surface tension is the dominant force, not the electromagnetic. It seems like in your paper, you indicate that electromagnetic, it's indeed important. But once the surface tensions and the Rayleigh instability, Rayleigh plateau instability, which divides the jet in droplets, yeah, this type of instability is really dominating. It's the force, and we applied the pulse of electromagnetic force, and afterwards, even the pulse force is now eliminated, but the surface tension kicks in, and the droplet is being pinched off very strongly, very fast by these surface tension forces. So you see, it's a very complex problem, but very interesting. So I congratulate you on this paper. That's really nice.
Yeah, thank you. It was Sabrina.
Yeah, but so our experience tells there's a lot of problems with droplets with electric currents, which had similar story.
Yeah, the thing is at MIT, they really built batteries with a short circuit, and I think then they got so hot that they were getting red by color. So really hot due to the short circuit, but in the end, no one knows why you had the short circuits. So they had short circuits, but we don't know why. We still don't know why. That would be good to find out, but whether it's such a small one or a big one caused by sloshy. We really don't know. And so these things, of course, they don't publish.
Yes, I know. That's the problem. We cannot tell because you need to know details. Yeah.
Yeah. So we have no motivation as they don't publish it.
Yeah, I agree. Yeah, but the short circuit is very bad anyway. It's devastating for the batteries. We need to avoid that. To confine it.
Top secret. I reviewed some article, which I should not communicate, but they basically simulated how hot will the battery get if you have a short circuit and what kind of thermal convection will arise. This I found also very interesting. What happens with such a short circuit?
It's very similar to solid state lithium batteries, which are heating up until they explode.
Here, I think they don't explode, but they get very hot. And of course, for us in the batteries, this is of practical importance because we need to care about such things.
So it again, the stabilization of the interfaces, and the top interface is very, very sensitive. Even if this is confined in a foam or some kind of mesh, there's still this possibility of dripping through. And if this is kind of enhanced effect by MHD, then what? Well, it's detrimental, definitely. We need to control that.
Excellent. Thank you, Norbert.
Thank you.
Any more questions from the audience, maybe? Okay. I think we don't have any questions on the chat. So feel free also to write some questions on the chat. Okay, well, if there are no more questions, I think we should thank again Professor Valdis Bojarevics for this very nice presentation. Professor, thank you very much.
All right, my pleasure to give something.
Sure. Well, thank you again, and thank you everyone for attending this seminar. Hope to see you soon on the screen. Thank you very much.
Thank you.
Thank you. Bye-bye.
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 Yeah.